So let's work on completing these tables. First of all, we're going to do column number 2. We're going to put down all of the radian measures, converting them to degrees. Now I want to show you a neat way to do this. So, for example, I know that 180 degrees is pi radians. Well, if I double that, I get 360, which is 2 pi. If I cut 180 in half, I get 90, so cutting pi in half is pi over 2. And 90 times 3 is 270. So 270 is 3 pi over 2. Now I'm going to do some of the other angles. I know that 45 is half of 90, or 45 is a quarter of 180. So 45 degrees in radian form then is pi over 4. And now I'm going to count by pi over 4s. So 45 is pi over 4. 90 is 2 pi over 4, which reduces to pi over 2. 135 is 3 pi over 4. 180 is 4 pi over 4. 225 is 5 pi over 4. 270 is 6 pi over 4. That reduces to 3 pi over 2. 315 is 7 pi over 4. So if I can count by 45s, I can count by pi over 4s, and I can get those values in. Another one to do is 60 degrees. So I know if I take 180 and divide it by 3, I get 60. So if I take pi and divide it by 3, it's pi over 3. Now let's count by 60s. Let's count by pi over 3s. 60 is 1 pi over 3. So 120 is 2 pi over 3. 180 is 3 pi over 3. 240 is 4 pi over 3. 300 is 5 pi over 3. 360 is 6 pi over 3, or just 2 pi. And then if I take 180 and divide it by 6, I get 30. So every 30 degrees, I go up by pi over 6. 60 is 2 pi over 6. 90 is 3 pi over 6. 120 is 4 pi over 6. I have all those already. I don't have 150, which is 5 pi over 6. I have 180. I don't have 210, which is 7 pi over 6. I have 240, I have 270, I have 300. I don't have 330. That's going to be 11 pi over 6. And let me show you another way now to remember the sines and cosines of those angles. I forgot one other one. 0 degrees is 0 radians. So remember that sine is the y value. So if the angle's in standard position at 0 degrees, the sine of 0 is 0. Now watch what happens here. If I'm remembering my 30, 60, 90 triangles, the sine of 30 is 1/2. The sine of 45 is the square root of 2 over 2. Sine of 60 is the square root of 3 over 2. So notice how those increase. The sine of 90, the y value is vertical, so, or on the angles in standard position, the y value is up at 1. And then it's going to go back down. Radical 3 over 2. Radical 2 over 2. Radical 1 over 2. Ooh, radical 1 over 2 is just 1/2. Then it goes to 0. And then it goes negative. Negative 1/2. Negative radical 2 over 2. Negative radical 3 over 2. Negative 1. Then it goes back up. Negative radical 3 over 2. Negative radical 2 over 2. Negative 1/2. Back to 0. Now, if we talk about the cosines, you saw that the cosines were really related to the sines, and we know a lot of relationships here. So the first relationship is that cosine is the x value. So when we're 0 degrees, cosine of 0 is 1. you might remember that the sine and cosine of complementary angles are equal. So the cosine of 30 is the sine of 60. Notice now from 1, we go to radical 3 over 2. Then radical 2 over 2. Then 1/2. Cosine of 90 is 0. And then we're going to go negative. Negative 1/2. Negative radical 2 over 2. Negative radical 3 over 2. Negative 1. We go back up. Negative radical 3 over 2. Negative radical 2 over 2. Negative 1/2. And 0. And then we become positive again. 1/2. Radical 2 over 2. Radical 3 over 2. And getting back to 360, we're at 1. So that's my way of remembering how to complete the table and also how to convert degrees and radians for those. These are values that you should know. You should know exact values of these sines and cosines and know the exact radian measures as well. But now let's get to some graphing. Let's graph the function f of x equals sine x. And we're going to graph it from 0 to 2 pi. So what that means is I'm going to draw my y-axis right over here. And I'm going to draw my x-axis going over this way. This is pretty typical of how we set up a trigonometric graph. I'm going to space it out here. I'm going to say like every 2 boxes is 1/2. Now, in terms of the horizontal axis, if you think about pi over 3 for a second, pi over 3 is pretty darn close to 1 because pi is a little bit more than 3. So what that means is that I'm going to put pi over 3 in about the same spot where I would put 1. So if my units go 4 boxes up to 1, I'm going to go 4 boxes over to pi over 3. So that's 60. So it looks like pi over 6 would be here at 30. And then I'm going to go to pi over 2. And typically we break it up into chunks of pi over 2. So it looks like every 6 boxes would be a pi over 2 interval. So let me go another 6 boxes to pi, another 6 boxes to 3 pi over 2. And if I spaced it out correctly, I should be out here at the end of 2 pi. Oh, that's beautiful. So that's typically how we do the spacing of it. Now, if you use the table that you created before, you might remember that the sine value goes from 0 up to 0.5, up to radical 2 over 2, which is about 0.7, somewhere around there. So it's a little bit lower than that. And then to about radical 3 over 2, which is about like 0.86. And then up at pi over 2, it's at 1. And then it starts going back down. Starts going back down a little bit. And at pi, the sine of pi is 0. And then we continue going back down a little bit more. Use the values on your table to help you plot some values. 3 pi over 2, the sine is at -1. And then it goes back up to 0 again. So this is what the graph of f of x equals sine x does. It's a nice curvy graph. Can you tell that it's almost comprised of circles as you went around that unit circle? Now, what's going to happen if the graph is, to this graph, if we go less than 0 for x, if we go off to the left? Well, we would just continue going down that way. Or if more than 2 pi, we would keep going up that way. This graph is what's called a periodic graph. It just keeps repeating itself every 2 pi, and we're going to address that a little bit more. If that's what the graph of sine x looks like, let's graph f of x equals cosine x. If you want to pause the graph or pause the video and graph it, sounds good to me. I'll wait for you. All right, welcome back. Let's do our same graph. Let's say that's up at 1, that's 0.5, negative 0.5, negative 1. Let's say that we said 4 boxes was pi over 3, so let's go 6 to pi over 2. And let's go to pi. 1, 2, 3, 4, 5, 6, there's pi. 1, 2, 3, 4, 5, 6. There's 3 pi over 2, and then another 2 pi. Now, if you take a look at that table of values that you have, you're going to see a lot of the same values. So the graphs are going to look pretty darn similar. We're going to talk about that in a second. Cosine starts up at 1, and then it starts going down. And the cosine of pi over 2 is 0, and then it's going to keep going down for a little while to -1, then it starts going back uphill. I think that one's up a little higher, yeah. That one's more like around there, that one's there, that's at 1/2. And really, when you start graphing some of these, what you're going to pick out are some of those key values. And some of the key values that you're noticing here are values like, when is it equal to 1? Or when is it equal to 0? Or when is it equal to -1? These key values in red, those are the ones that if we remember, we can sketch the rest of it. So this is the graph of y equals cosine x. And it looks pretty similar to the sine graph. And what you might notice is that really what we're doing is we're taking the sine graph and we just shift it left a little bit. So if I could go back this way, it would end up somewhere down at 0. We just kind of slide the sine graph to the left and we get the cosine graph. That's pretty cool. And that should make sense because we know that the sine of an angle equals the cosine of its complement. All right, good graphing there. Boy, oh boy. So again, we call these functions periodic functions because every interval, over a certain interval, they repeat themselves. So what you noticed was for the period of sine x and for cosine x, its period was 2 pi, meaning that it does one cycle of the graph every 2 pi. So let's go to our graphing calculator and graph this. That's what we call our GDC, our graphing display calculator. So I'm going to go to my calculator. I'm going to graph f of x equals sine of x. Let's press enter. Sure enough, you can see how it's a periodic graph. It kind of goes from left to right. It's going down and going up and going down and going up and going down and going up. I'm going to edit a few things on this graph. What I'm going to do is I'm going to change my minimum value here by double clicking on it. Let's call it 0. And I'm going to change my maximum value. Can I get to that maximum value? There we go. Let's do that to 2 pi. Watch this. If I type in 2 pi, it knows what pi is. And I'm going to make this maximum y value a little bit smaller. Maybe I'll make it like up to 3, let's say. And we'll make the minimum down to -3. So that's a nice looking picture of what the sine graph looks like. Can you tell what its domain is? Because it's a periodic function, the domain is all real numbers. And can you tell that the range is between -1 through 1? So we're going to write that in like an interval format maybe. Or we could say its range is between -1 and 1. Typical for sine, typical for cosine. Well, let's play with other graphs too. Graphing is fun. Take a look at these 4 new functions. What I'd like you to do is I'd like you to type them into your calculator. You can do it on the same one that you have the sine graph, because I want you to compare the changes that we've made in each function to the actual sine graph. I'll pause and I'll wait for you to do it. Okay, welcome back. So I put that one on this here. And look at all the different graphs that we have. Holy cow, it's a beautiful picture. Let's go through one at a time though. Let's compare the blue graph, which is the sine graph, to function g, which was 2 sine x. Can you tell now that the height of the graph, instead of going between -1 and 1, the range is from -2 to 2? And likewise, the black graph, when the number in front was 1/2, it only goes up to 1/2 and down to -1/2. The range is from -1/2 to +1/2. The pink graph is negative sine x. We take the blue graph and flip it over the x-axis. And the cool one, though, is the green graph. Look at this green graph. It has 1, 2 cycles in our 2 pi interval. So that 2 is doing something a little bit different. So let's define some of those terms for us. When we have a graph for like a sine bx, or for y equals a times cosine bx, it doesn't really matter if we do sine or cosine, the same rules are going to apply. The amplitude of the graph is its height. And the amplitude is measured by the absolute value of a. So notice back here that for the pink graph, when the amplitude was, or when the a value was -1, the range was still between -1 and +1. So the amplitude gives us the height of the graph. The frequency is how many do we see? How many cycles do we see in 2 pi? And that's our b value. So if I go back to my graphs for a minute, take a look at the green one. The b value is 2. So in a 2 pi interval, I see 2 cycles. Whereas in the other ones, the b value is 1, so I only see 1 cycle. And finally, the period. We defined the period before. The period was how long 1 cycle is. So that's kind of like the reciprocal, if you will, of the frequency. So a standard frequency, a standard period is 2 pi, but if we divide it by our value b, that's how long 1 cycle is. If I go back to my green graph for a minute, 2 pi divided by 2 is 1 pi. So every pi, I see 1 cycle of the graph. And that's going to be helpful when we want to sketch these graphs. Because if we want to take a look at example 9 on page 525, where we sketch this graph, knowing the amplitude and the period is very helpful. So from 0 to 2 pi, maybe our graph is going to look something like this. The amplitude is 3. So what that tells me is that it's going to go up to 3 and go down to -3. And let me put a couple other things on here too. So this is like where pi over 3 would be. I'm going to go a little bit further. So that's where pi over 2 is going to be. And then that interval again, maybe pi would be there, and maybe 3 pi over 2, and maybe 2 pi. That looks pretty good. So my amplitude is 3. Since my b value is 2, it tells me that the period is 2 pi divided by 2, or pi. So the b value tells me I'm going to see 2 cycles of the graph. The period is pi, meaning I'm going to see 1 cycle of this cosine graph every pi interval. So I know some key values for my cosine graph. I know cosine starts up at its amplitude. It ends at its amplitude. In between there, it's down at the bottom. It's the opposite of the amplitude. And in between those two, it's at 0. So 1 cycle of my graph is going to look something like this. And notice I didn't draw it like a V. It's not a V graph. It's a curvy graph. It's a circular function. And let's do it again with the next one. I'll plot some key values that I know. That one looks like it's about right there. And then it's up here again. So this is a pretty darn good sketch as to what y equals 3 cos 2x would look like. Again, the period is the period is pi, 1 cycle every pi. From 0 to 2 pi, we see 2 full cycles. That's our frequency. The amplitude is 3. Let's go the other way. Example 10 on page 525 was finding the equation of this graph by writing down the period and amplitude. Try to do it on your own. Pause it and wait. Hey, welcome back. So when I look at this graph, I think, okay, it's starting at 0, so it's a sine graph. The amplitude looks like it's up here. Maybe that's like 0.5. So the amplitude is 0.5. It looks like from 0 to 2 pi, I see 1, 2, 3 cycles. So I know my B value is 3. So that means the period is 2 pi over 3. Remember, we always divide 2 pi by our B value to get the period of the function. And again, we recognize it's a sine graph because it's starting at 0. So how about the equation y equals 0.5 or 1/2? Nope, not cosine. Sine 3x. Graph it on your calculator. See if it matches. It does. Celebration, friends.